into vectors. Oh, how come, what? We're going to get into vectors, then we're going to do some polar. Stay there. And then we'll get into sequence and series, which is usually a pretty tough chapter. But we're going to find the limit using L'Hopital's rule. We've already covered this kind of informally. I said, hey, this thing exists, you can use it. But now we're really formally looking at L'Hopital's and all its uses. So find using L'Hopital if necessary. We're going to plug 4 in. We're going to get 16 minus 16 over 4 minus 4. And we get what's called an indeterminate form. The 0 in the denominator is really the problem. But then if the numerator is also 0, then we have what's called an indeterminate form. The limit still might exist. It might not exist still. But every time we use L'Hopital's, AP likes us to note that we're going to use L'Hopital's rule now. And it's derivative over derivative. So limit as x approaches 4 of 2x over, well, the denominator is 1. Don't have to write over 1. But now that's 2 times 4. The limit is 8. Now, I'm not claiming that L'Hopital is the only way to do this. As a matter of fact, if we would have done this in the first chapter, we would have just factored x plus 4, x minus 4 over x minus 4. Those cancel. 4 plus 4, still get 8. But you can use L'Hopital's. I find that L'Hopital's is usually the easier way to do it when you get an indeterminate form. Over on the right here, if we plug 3 in, we get 9 minus 6 minus 3, which is actually 0. But then we get 9 plus 6 minus 4, which is not 0. 0 over 11 is 0. The limit is 0. If we did L'Hopital's rule, it'd be 2x minus 2 over 2x plus 2. When we plug in 3, we get 6 minus 2 over 6 plus 2, which is 4 over 8, which is a half, which is wrong. Unfortunately, L'Hopital's rule does not work when you don't have an indeterminate form. I wish it just worked all the time, but it doesn't. You have to check it first. You got to make sure that you get that 0 over 0 if you're going to use L'Hopital's. Use L'Hopital's rule to find each limit. If I plug 0 in here, I get sine of 0 over 0. Sine of 0 is 0. Cosine of 0 is 1, though. So we get an indeterminate form. We can use L'Hopital's. Limit as x approaches 0 of 3 cosine of 3x over 1. Derivative of sine is cosine. Derivative of the inside is 3, so 3 cosine of 3x. So we get 3 cosine of 0. 3 times 1 is 3. This isn't the only way to do this one either. If you have sine of 7x divided by 7x, that's always, well, as long as those two numbers are the same, it's always 1. So let's see, the window, I want negative, I don't know, negative 10 to 10, I guess. Go by 5, that's fine. Negative 2 to 2, graph. It is 1, you just can't see it. Let's see. Let's try this. Negative 1 to 1. There you go, now you can see it. So what we can do on this one is do the limit as x approaches 0 of 3 sine of 3x over 3x. I can multiply the top and bottom by 3. But just this piece goes to 1 right here. So this ends up being 3 times 1. You still get an answer of 3. Just have to make those the same. 5x, sine of 5x over 5x, that's 1. Limit as x approaches 0, of course. L'Hopital is probably a little easier to remember. It's kind of this blanket rule. As long as you get an indeterminate form, use L'Hopital's. 1 minus sine of pi over 2 is 1. Cosine of pi is negative 1. So you get 0 over 0. All right, so now we know we can use L'Hopital's rule. Limit as theta approaches pi over 2 of negative cosine of theta over negative 2 sine of 2 theta. The ones go away. Derivative of 1 is 0. Let's plug pi over 2 in. Cosine of pi over 2 over negative 2 sine of pi. We plug pi over 2 in, cancels out with the other 2. But cosine of pi over 2 is 0 and sine of pi is 0. So now we use what's called the stronger version, or however the book puts it, the stronger L'Hopital's, which means just do it again. As long as you get indeterminate form, you just keep doing L'Hopital's. So we have limit as theta approaches pi over 2 of sine of theta over negative 4 cosine of 2 theta. Right, sine, derivative of sine is cosine. Multiply times 2 again. Got it. So now we have sine of pi over 2. That's not 0, that's 1. Over negative 4 cosine of pi. That's not 0 either, that's negative 1. So the answer is 1/4. Well, I mean, the book says use a graph to support your answer. We don't have to do that every time, or actually in your assignment, you don't really ever have, I don't require you to do this. But let's do it once. So 1 minus sine of x divided by 1 plus cosine of 2x. The graph should be good because it's leveling off to 1/4 graph, so it should eventually, there you go. Are you convinced it's leveling off to 1/4 a little bit anyway? All right. Seems to be as you go left to right. Going to actually 2 pi over 2. Discuss graphs of these functions. We're going to be asked stuff like what is the limit as x approaches, let's see, what, pi over 2 from, let's say, pi over 2 from the left of secant of x. And you're going to have to be able to know what that is. It's positive infinity. But the graph of secant starts with cosine. Wherever cosine is 0, that puts 0 in the denominator of secant, so we have vertical asymptotes. And then in between the asymptotes, you turn cosine upside down. So this is the graph of secant. Now if it said, what's the limit as x approaches pi of secant of x, I wouldn't think about the graph, not right away. Only if I have to. I would say, well, cosine of pi is -1, reciprocal of -1 is -1. So this is -1. But that's on the graph there. You can get it from the graph as well. This is cosecant. It's the reciprocal of sine, so you graph sine. Wherever sine is 0, we have vertical asymptotes. And then I wouldn't think of the graph first. I would think of what is sine, and then I'd go from there. But if sine is 0, then I know that cosecant has an asymptote there, and I'd have to decide whether it's positive infinity or negative infinity. So I don't think of the graph first. I think of it only if sine or cosine is 0 there. Then you got to think about, well, now what does the graph look like? This is tangent. We usually graph the denominator. So sine over cosine, right? Sine over cosine. So we graph cosine, and then wherever cosine is 0, tangent will have a vertical asymptote. This is cotangent, so we graph cosine, we graph sine. Wherever sine is 0, cotangent has that vertical asymptote. And the nice values that we have for tangent and cotangent are -1 at the pi over 4s, 0 and 1 at the pi over 4s. So negative 1, 0, and 1 are usually the values we work with when looking at tangent and cotangent. This is the natural log of x. So the limit as x approaches infinity of the natural log of x is equal to infinity. This does go up forever, but very, very slowly. Very slowly. And the limit as x approaches 0 from the right of natural log of x is negative infinity. As you approach 0 from the right, we're going down to negative infinity. This is the one where I made the little video. It has like 18,000 views. All my others have 500 maybe. This is probably the 10th year for some of those videos. So that one blew up for whatever reason. Pretty cool, I think. This is inverse tangent. And with inverse functions, you switch x's and y's. So this is the pi over 2's. And over here, that's the 1 and the negative. Well, yeah. Somewhere around there. I suppose that probably is the 1 and the negative 1. Now we use this a few times, not a lot, but limit as x approaches infinity of inverse tangent of x is equal to pi over 2. This one levels out to pi over 2 on the right. And the limit as x approaches negative infinity of inverse tangent is equal to negative pi over 2. Now, we don't use that 100 times. We use it a couple times. You might run across that in a couple problems that we do. You know, it's tangent. There it is. We looked at tangent. This is pi over 2. This is negative pi over 2. So we switch the x's and the y's for inverse. Pretty heavy stuff for first day back. All right, now how do we use some of this? The tangent of 0 is 0. So we have 0 over 0. So that means I can use L'Hopital's. Limit as x approaches 0 from the left of secant squared x over 1. So I need secant squared of 0. The secant of 0, let's see, that's the reciprocal of the cosine of 0. Cosine of 0 is 1. So it's really 1 squared. 1 squared, which is 1. I wrote equals twice. Because the denominator goes away, I can use L'Hopital's here. Tangent of 0 is 0 over 0. Limit as x approaches 0 from the right. It doesn't really matter that we're on the right or the left here because the denominator is gone. Secant of 0 is still 0, or excuse me, 1. 1 squared is 1. So it really didn't matter that we're on the left or the right side for that one. On number 12, it does matter. So this is still 0 over 0 squared is still 0. So we do L'Hopital's. Limit as x approaches 0 from the left of secant squared x over now 2x. We have to deal with a variable in the denominator now. So secant squared is 0 over, it's kind of 2 times 0, but we can't plug 0 in the denominator. This is really 1 over 2 times, not really 0, because we can't plug 0 in, but we can approach 0. That's what limits are, approaching a value. But we're approaching 0 on the left side, so negative 0.0000, something very close to 0. Infinitely close to 0, but negative. So this is negative infinity. If you take 1 divided by an extremely small number, you get a very big number. Well, we're approaching infinity, except it's negative on this one. This is 0 over 0. I can do L'Hopital's. So we have the limit as x approaches 0 from the right of secant squared over 2x. That's 1 over 2 times something really small, but positive now. We're on the positive side of 0. So this is going to positive infinity. So it did matter whether we're on the left or the right side for this one. Not the other one. Denominator went away. No problem. Same answer. No problem. Here it matters. Any questions? All right. So you got to decide on, there's 2 others you have to do. You decide if it really matters or not if you're on the left or the right side. All right, a little bit more practice. We have square root of 9 minus 3 over 7 minus 7. 3 minus 3 is 0 over 0. All right, so now we can use L'Hopital's. We checked. Limit as x approaches 7 of, let's see, this is 2 plus x to the 1/2 power. That's what that is right there. So the derivative is 1/2, 2 plus x to the negative 1/2, times the derivative of the inside, that's 1. We have 1 over 2 square root of 2 plus x. Derivative of negative 3 is 0. Derivative of x is 1. Derivative of negative 7 is 0. So now we can plug 7 in. 1 over 2 times square root of 9, so 1/6. So if you graph that at 7, it's approaching 1/6. It can't be 1/6, but it can approach it. E to the 0 minus 1 minus 0 over e to the 0 minus cosine of 0, that's 1. So 1 minus 1 over 1 minus 1, so 0 over 0. That's an indeterminate form, so we can use L'Hopital's. Limit as x approaches 0 of 3 e to the 3x minus 3 over 2x e to the x squared plus sine of x. So e to the x squared, derivative of that is e to the x squared, but then times the derivative of the inside, that's where the 2x comes from. Now if we plug 0 in, e to the 0 is 1, so we get 3 minus 3, e to the 0, 1 times 0 is 0, sine of 0 is 0. 0 over 0. We get to have more fun. Limit as x approaches 0 of 9 e to the 3x over 2x times e to the x squared. That's a product of 2 functions. So we have to use the product rule. First times the derivative of the second plus the second times the derivative of the first. Product rule for that. It's 2 functions multiplied. And then plus cosine of x. The good news is we're plugging 0 in. Plugging 0 in is usually pretty easy. There's no negatives, you know. Don't have to worry too much about negatives and all that. So this is usually pretty easy. This first piece will be 0. Excuse me, I should do the top first. 9 times 1. That'll be 0. 2 times 1, and then plus 1. Cosine of 0 is 1. So 9 over 3. 3. Anyone ever seen that old commercial, how many licks does it take to get to the center of a Tootsie Roll Tootsie Pop? The wise old owl. 1, 2, 3. 3. I thought we could do a little preview of tomorrow. We ain't going anywhere. Might as well. The difference here is we have infinity. If you look at all the other limits that we looked at, none of them are infinities. Some answers we got are infinity, but no limits. They're all values. So let's look at what we're going to do tomorrow. And the more you see it, I think the better off you are. So you won't have to do something like this in your homework, not for today, but tomorrow. The problem here, well, let's look at the indeterminate form that we have. We have 1 plus 1 over infinity to the 3 times infinity. Well, what's 1 over infinity as a limit? What are we approaching? 0, right? Denominator's getting really big, fraction's getting really small. So this is 1 to infinity. You would think it would just be 1. 1 to anything's 1, but not when it's infinity. So this is an indeterminate form. I want to get that variable out of the exponent. So here's what we do. We create a fraction, which is illegal in most states. That's legal in Nebraska for now, but as long as we undo it in the end. We got to undo this. If we introduce the equation, we got to get rid of it in the end. Hide the evidence so we don't get arrested. Now we're going to take the natural log of both sides because we can now remove that power. We can put it in front. Take the natural log of both sides. Now 3x can come down here. Let's introduce the limit again because we're evaluating this. So limit as x approaches infinity of, oh, I need a fraction. If you take, how about if you take, I don't really need a calculator for this, but if you take 2 times 6, you get 12. You ever heard of, instead of dividing, you can multiply by the reciprocal? Well, instead of multiplying, you can divide by the reciprocal. So 6 divided by 1/2. Whoops. 6 divided by 1/2, that should still be 12. Okay. 6 divided by 1/2. There we go. If you use parentheses, it still is. It's still 12. So we're going to create a fraction here by dividing by the reciprocal. We're going to do natural log of 1 plus 1 over x over 1 over 3x. That's the same thing. It looks different, but it'd be the exact same value. Multiplying, dividing by the reciprocal, same thing. We've already decided that this is an indeterminate form, so we can do L'Hopital's now. So we have limit as x approaches infinity of 1 over 1 plus 1 over x. Derivative natural log of x is 1 over x, so you take 1 over whatever's in there. Times the derivative of the inside. Well, the derivative of 1 is 0, so I need the derivative of x to the negative 1. That's negative x to the negative 2. So times 1 over x squared. There's the derivative of the natural log part. Now we need the derivative of 3x to the negative 1. Okay. So negative 3x to the negative 2. So that's going to be over negative 1 over 3x squared. Oh, what'd I forget? Oh, yeah, I forgot the negative there. And I forgot the chain rule. Times 3. Times 3. Shame on me. I even forget it every once in a while. I didn't forget last period. That's the weird part. Limit as x approaches infinity of 1 over 1 plus 1 over x times negative 1 over x squared over, this is really 3/9. 3/9, so negative 1 over 3x squared. So now we have some algebra to do. I got to clean all that up. Let's multiply by negative 3x squared on the top and the bottom. Let's do that first. Limit as x approaches infinity of 1 over 1 plus 1 over x. These cancel, and negative times a negative is a positive, and these all cancel over 1. So what you're left with is 3, right? We're left with 3. Now we can actually plug infinity in, believe it or not. That's 1 over, actually 3 over, let's make it 3. 3 over 1 plus 1 over infinity. Well, what's 1 over infinity as a limit? What are we approaching? 0. So we have 3. Now remember we said that we introduced the equation, and now we kind of got to get rid of the equation. What we have on the left side, we just worked with the right side. What we have on the left side is natural log of y equals 3. So natural log is base e. So e to the third is our answer. So e to the third. And it's not an equation, it's really just a value. We introduce the equation, we get rid of the equation, we just end up with a value. E to the third is the answer. Questions? Well, we're still going to do that tomorrow, but I thought I'd give you a little sneak peek of it.